everyone, to welcome to the first panel of today. My name is Martin Laforest. I'm the Senior Manager of Scientific Outreach at the Institute for Quantum Computing at the University of Waterloo. So we've heard this morning already from Dr. Milner and Dr. van der Verden that quantum computing it's quite a thing. It has a potential to be very disruptive. It can have some application to great problems that we have. It can also bring some threats, just like any other disruptive technology. But quantum computing is not the only thing that quantum mechanics can give us. So what we're going to do in the next hour or so is we're going to dig down a bit more on, well, maybe a bit more what quantum computing is and what it can do, both benefit and threats. And then we might also hopefully have time to go a little further than quantum computing and talk about maybe quantum sensors, quantum simulations, so other application that using the laws of quantum mechanics can give us. So we have assembled a very nice panel here today. A variety of expertise, variety of experience, and we're going to try to cover many different facets of quantum computing. So first to my right is Professor Kris Munroe. Professor Monroe is a distinguished professor at the University of Maryland, and he's also a fellow at the Joint Quantum Institute, which is a joint venture between the National Institute of Standards and Technology and the University of Maryland. More recently, he is also the co-founder and chief scientist of IonQ, which is a startup company looking at building universal quantum computers based on ion trap. Professor Monroe is a pioneer in experimental quantum physics, and he's been a leader in the field pretty much since there's been a field. So lots of expertise there. So and today he's going to talk to us about the power of quantum computers, some of the different type of applications, and also going to give us a bit of a survey of where the technology stands. Like where are we in the quest of building a quantum computer? Next to him we have Michael Brett. Michael is the co-founder and CEO of QBranch, which is a company that focuses and specializes in software tools for quantum computing for advanced analytics and applications to finance, insurance, aerospace, security, and many other applications. Prior to QBranch, Michael was the COO of Scholl Electronics, and today he's going to talk to us about what quantum computing can do for data analytics. He's also going to give us a bit of a commercial landscape of where quantum companies are around the world, and he's also going to talk about the type of organizations that are interested in those quantum software tools. And then finally, we have Dr. Altaf Carim. He is a physicist at the Office of Science of the U.S. Department of Energy. So he has an extensive experience in the federal service. He joined the DOE in 2001. And he actually just came back to the Department of Energy after serving about 6 years as an assistant director at the White House Office of Science and Technology Policy. And prior to that, he was also a faculty member at the Penn State University. And he's going to talk about sort of what's going on here in the United States, the interagency coordination and approach to quantum information. And he's going to give us the DOE vision and motivation in quantum information, but applied to quantum computing, but also for quantum sensors, simulation, and other type of application. So what we're going to do is for the first 45 minutes or so, each panelist will present for about 15 minutes, and then we will open the floor to questions. So please get your pen and paper, write down some questions, because we'll have plenty of time, and hopefully get some discussion going. So I'll invite first Dr. Kris Munroe.
Thank you, Martin, and thanks for the opportunity to be here. So I'm going to step back a little bit, not to do pedagogy for pedagogical sake, but when you look at the fundamental tenets of what a quantum computer is, it offers great hints as to what a quantum computer can and cannot do, and finally, how you might try to build one and the various pitfalls, and I'll use the word exotic a lot, the exotic hardware that you're confronted with. So when I teach quantum physics these days, it's not just a physicist, and this is very nice, and I teach it from the perspective of information theory, and we had a nice introduction from Warner and also Aaron. on what qubits are. Basically, anything that has two states and it's quantum, that's the trick, can be a qubit. And qubits, as Warner said, can be in a superposition of both 0 and 1 at the same time, and that's where it radically departs from our concept of classical information. And furthermore, when you put lots of qubits together, the system gets very complicated very fast, because it takes, with one qubit, in a sense, you can store two numbers. With two qubits, 4 numbers, 8, 16. You have this inherent exponential growth. And pretty soon the numbers get ridiculously large, and one I like to choose is 300. If you had 300 quantum bits and complete control of these quantum bits, there would be 2 to the 300 configurations, all in superposition. And that number is interesting because 2 to the 300 is also about 10 to the 90. This is more than the number of particles in the universe. So merely with 300 photons or 300 atoms, given that you can control them, you would be capable, and there's a big footnote here, there's a big catch on how to do this, you'd be capable of doing things that you could never, ever do, even if every part of the universe is part of a regular computer. Okay? So you might turn this around and say, well, if we're going to deal with not just big data, but huge data, we will have to confront storing this in a quantum system. That's a little speculative, but clearly the opportunity is there. So I think of quantum mechanics from a pedagogical point of view as having 2 and only 2 rules, and they're very easy to state. The problem is in physics, especially in physics, we like to have one rule at the very top and everything falls from that. In quantum mechanics, we can't do that, unfortunately. We have 2 rules at the very top. And the first one is this idea of a superposition, that quantum systems are waves. You've heard this. There's a wave equation, which, again, is nothing very complicated. A wave equation we're very comfortable with. Sound waves, water waves. In fact, the idea of a superposition is not such a big deal. When you hear multiple musical tones, you hear them in superposition on your eardrum. So we're comfortable with any wave-like phenomena having a superposition. It's the second rule that's strange when taken together with the first rule. A quantum wave is a very special one. It's a wave of the reality of the system. It's a wave of probabilities. The second rule says that, yes, this superposition persists as long as you don't look at it. As long as nobody looks at it, as long as the system is isolated and is not interacting with its environment. And this is very strange on 2 counts. The first count appears that the mere act of looking at something changes that something. And this bothers everybody that studied quantum physics, starting with Einstein, I would say. But I would say get over it, because it turns out that if you want to complete it and find out if there's other things going on, it will be at least as strange. Even though I'm in the field, I do read popular quantum books. They're a lot of fun. I recommend doing it, but don't get stuck in it. These rules are here to stay. Okay. The second weird thing about rule number 2 is that when you do look at a superposition of many possibilities, it randomly pops into one and only one result. And it's described by the language of probabilities, which, again, we're used to using probabilities in all kinds of the physical sciences and economics and so forth. But in all other theories of nature, probabilities express ignorance. When you toss a coin, we don't want to know exactly how hard we tossed it or what the local value of gravity is. So we use probabilities to sort of cast away our ignorance. Now, in quantum mechanics, probabilities, it's not about ignorance. You have to use probabilities. It's the only theory where probabilities is right there at the top line. And this is very strange. When you think about it, probabilities are strange, in a sense, any probabilities. But in quantum mechanics, they're very strange because we have no idea where they came from. It's not ignorance. So with those 2 rules, we can sort of get a hint at what a quantum computer might be good at. Why is that? Well, if we take 2 to the 300 inputs, that's 10 to the 90 inputs, you might say, wow, that's a lot of parallel processing. I can compute the logarithm of every of those inputs all at the same time. And in a sense, yes, you can do that. But then you need to look at it. You need to measure it. What kind of computer is one that you can't read? You can't read out. So the problem with a one-to-one function like log of x or the square root of x is that, yes, you get to compute all those, but when you make a measurement, you only get one random output, and you don't even know what input produced that output. So one-to-one functions, unfortunately, are out, and doubly unfortunately, one-to-one functions are mostly what we do on our laptops. So good quantum applications typically, well, I would say always, everyone that I know, they take all these inputs and they sort of, there's a forcing function at play or some winnowing down to maybe one answer or maybe a few answers, but not 2 to the 300 answers. Maybe 300 answers, maybe one answer. If it's 300 answers, you still have some randomness, but you could repeat the experiment 300 times. That's not so bad. Or a few thousand times. You're never going to repeat something 10 to the 90th time. So forget about one-to-one functions. So the factoring algorithm was mentioned prominently this morning. And it turns out with 2 lines of number theory, it's very simple actually, the factoring problem can be turned into a problem of finding the period of a function. I think Aaron mentioned this. A certain function repeats itself. When you plug in all the inputs, you can find out when it does. And that period, it turns out it can give you information on the factors of a big number that is encoded in that function. Finding the period of a function is not something that we typically think of as hard. For instance, when you play the middle C on your piano and you hear that, you can identify, oh, I know that's a middle C. It's a sine wave function, and even the sine wave function, just by writing it down, we know the period. But there are other functions where the period is not so obvious, and factoring exploits one of those. Another class of, and Aaron said it'll probably be the last algorithm to be demonstrated because it probably requires millions, maybe billions of qubits in operations. But there's a more interesting and less esoteric application. Unfortunately, it's maybe magic is a good term to describe it. It's optimization. Now, quantum computers are generally good at finding global properties of huge data. Well, if you want to find the minimum of some complex function of many variables, that minimum is a global property of every input. It's not a one-to-one function, finding the minimum. If you want to find the tallest peak in the Rockies, you have to look at the entire map. You have to look at every square foot of the western U.S. Now, finding maxima and minima of complex functions, this is an incredibly important problem everywhere from logistics to cost savings to understanding economies and markets. It's a big deal. Unfortunately, we don't believe that a quantum computer can find the absolute minimum of a function, but it may be able to, and this is very active research, it may be able to find a very good approximation to a minimum, an approximation that's better than any classical computer because it just deals with huge amounts of data. So I look at that problem as actually being the one that will happen first. And again, I'm being vague because we don't really have a killer app. And my feeling as an experimentalist is that we have to build it first and see how it works and have it tested in a variety of contexts. Okay, so finally the hardware. These rules, they sort of tell you how to build one and how not to build one. Well, here's a hint. Don't build a quantum computer if it's coupled to the outside world. Now, remember, the superposition principle allows any quantum system to be in 2 states. I can take this remote control in principle and put it in 2 places at the same time, as long as you don't look. And so that means you have to close your eyes, but we also have to isolate this thing from everything, including the air in this room and so forth. Pretty exotic to do that. Now, it doesn't require a theory of consciousness to understand this rule number 2, measuring something affects things. Because consider there's no conscious being in the room, but this remote's in 2 places, and there's a single air molecule. And it's like we're traveling along where my finger's pointing. Well, this air has to decide, am I going to hit the remote, or am I going to go and hit the back wall? Am I going to bounce off the remote and hit that wall, or go through and hit that wall? Well, quantum mechanics, the way we deal with this is we invite the air to be part of the system. So now we have a superposition of remote control here, air bounced, hit that wall. Superposed with remote control here, air went that way. And it doesn't stop with the air molecule because now the air has to decide the wall has to decide which one gets hit. The building, which way it shakes, the whole Earth, the whole universe inevitably gets involved. And so we don't like to do that in quantum mechanics. We cut off the system and say this is isolated. And that's what we mean by having a system that's fully coherent. It's not measured. So we look for hardware in quantum computing that is indeed isolated to the extreme. And so you'll hear maybe later today about some candidate hardwares that come from very weird physics, esoteric effects. The technology I work with involves individual atoms, one at a time, that are held in a vacuum chamber, so there's no air. They're levitated over electrodes, so they don't touch a surface. These are pristine quantum systems. They're scalable in the sense that each atom is exactly the same because they're the same isotope of a particular element. They're in fact atomic clocks. And you can repeat that. That's a good clock. You have to be able to replicate. So it's scalable in that way. There's another, I would say there are two leading technologies and a few others that are still more in the research phase. The other leading technology is superconducting circuitry. Now, superconducting circuitry is current. These are basically currents that flow without loss. In other words, the electrons that contribute to that current don't bounce into things. It's sort of a magic of a different sort. It's a very neat physics effect. When you get things very cold, many materials have this superconductivity feature. And you can simply wire them together with superconducting wires and so forth. And we'll hear some more about that technology. And this is what many of the behemoths are building, Google, IBM, and so forth, superconducting circuits. They're scalable in a different sense. And it's complementary. They're not fundamentally scalable because every superconducting circuit's a little different. And when you make the system big, those little differences really start to matter. On the other hand, they're printed on a circuit. We're a little more, if you want to think of a computer, you usually think of a two-dimensional thing that where you grow a circuit on top of it. So if that's your definition of scalability, then it's interesting to look in that direction. That's one thing you should keep in mind. The concept of scalability is an incredibly complicated concept that means something different to everybody. So beware. If somebody says it's scalable, you need to dig deeper. So I think that's all I wanted to say, except what's lovely about this field, again, there's always a pedagogical start to it. They're very weird rules, and if you can get by them, they can not only guide you to understand maybe how quantum computers can be applied, but also how to build them. Thank you.
Thank you, Christopher. Our next presenter will be Michael Brett, CEO of QBranch.
Thank you very much, Martin, and good morning, everybody, and thank you for the opportunity to speak with you today. I'll hopefully shift gears a little and get out of the quantum physics space and the quantum hardware space and share with you a little about what we've learned about the applications of quantum computing and where we think that's headed over the next couple of years. So my company, QBranch, we are a data analytics company. We specialize in predictive analytics in particular. And entirely in the commercial space. So we're working with banks, with insurance companies, with other technology firms on problems like pricing and understanding risk and customer behavior. And a lot of the technologies that we bring to this are in the classical domain today, but we see quantum computing as a long-term strategic differentiator for what we do. A lot of the work that's involved in complex pricing and complex risk requires a lot of computational power. We're building machine learning algorithms. We're starting to get into the realm of AI. And the amount of computational effort that's required to create those algorithms and to study that amount of data is enormous. And so we see quantum computing as a key to potentially unlocking some of the things that we want to do in the future. So if you think of Kris and IonQ at his company and the other hardware companies, they're doing the bottom-up effort from the lasers and the atoms to the superconductors and the circuitry and the control systems that abstract away from that hardware. Companies like mine are doing the top-down effort, trying to understand what the use cases are, the kind of problems that we need to solve out in industry, and hopefully we'll meet in the middle somewhere and be able to complement each other's efforts. I think this is actually your line, Kris, so if you don't mind, I'll steal it, that if we can't show value out of a 30-qubit system, then no one's going to give us the money to build a 300-qubit system. So we need to be able to show that pathway to commercial outcomes from quantum computing and how that fits into existing problems today and what we can do with that. So I want to paint a picture of the future and where we believe quantum computing is headed from a hardware perspective and an accessibility perspective. So the major investments into quantum computing hardware over the past couple of years have all come from the major cloud services providers. So IBM, Microsoft, Google, Alibaba made some big announcements last week, Intel as well. Quantum computing will manifest in the cloud. We already today see a mixed hardware environment in the cloud. If you go to AWS or to Google, you can buy time on CPUs and different types of CPUs. You can buy time on graphical processing units, GPUs, made by companies like NVIDIA. Soon you'll be able to buy off Google Tensor processing unit time for their software application TensorFlow. And what we're seeing is that each cloud services provider is providing specialist hardware for particular problem sets. So if you want to do mass parallelization, the best hardware to run that on is GPUs. Very high degree of precision. You can start to solve problems that are particularly related to machine learning. If you want to solve TensorFlow and create AI with Google in the most efficient way possible, then the tensor processing units are the most effective way to do that and the most efficient way to do it. And we see quantum computing sitting as a complementary device in that mixed cloud compute environment. So the cloud of the future will have CPUs and GPUs and TPUs and QPUs, quantum processing units of various kinds, some built by IonQ, some built by Google, some built by D-Wave, some built by Rigetti. What we want to see is a mix of quantum computing infrastructure that all provides usefulness in different ways for different applications. So at your companies or your organizations, when you're designing algorithms and trying to solve complex problems, you'll use a cloud compute environment. You'll go to AWS or Google, pay with a credit card to get access to niche computing capability. And that cloud compute environment will allocate the right algorithm to the right hardware. Some of it will run on CPU, some of it will run on quantum processing units. And together, that will provide value to the enterprise or your organization. But we've got a problem. The problem is that programming a quantum computer is hard. It's incredibly difficult for a regular software engineer or regular data scientist coming out of the current programs at their universities and with their experience base so far to pick up the tools of quantum computing and start to design those applications. And so what we're doing at QBranch and in partnership with a few others is building the toolkits that bridge that gap, that make it easy as possible, as accessible as possible for regular software engineers to create applications with quantum computing and to be able to access the types of hardware that Kris is building and deliver benefit from that. So I'll give you a quick example of some of the work that we're doing in the commercial sector. One of our lead customers is Australia's biggest bank, the Commonwealth Bank of Australia. CBA is, I think, also one of the top 10 banks in the world, and they're regarded as being the most forward-leaning technology bank in the Asia-Pacific region. They've made significant investments into a range of emerging technologies, including blockchain and AI and a few other things, but importantly, quantum computing. Over the past 5 years, they've invested something in the order of $20 million into quantum computing research, but also very recently a quantum computing hardware company based in Australia called Silicon Quantum Computing. They put $14 million as effectively part of its Series A investment into a quantum computing hardware company in Australia. And they describe quantum computing as essential to its mission of deepening their relationship with their customer, which is kind of an odd thing for a bank to say about a technology like quantum computing. But what they mean by that is the relationship that a bank has with its retail customer is all about trust and all about understanding of your needs. And the amount of data that is generated by your transactions and other people's transactions, they want to be able to make the best possible use of that to deliver value to the customer and also ensure that you continue to trust the bank with your money and to support those the transactions that you do day to day. So they're investing in high-performance technologies like quantum computing to look out on a 5, 10, 20-year time horizon about the kind of applications that they need to deliver around optimization, machine learning, customer behavior, pricing, and risk that can then support the kind of products that we use day to day. What we do with the Commonwealth Bank is help them develop that workforce. So within a technology organization like a bank, how do we get regular software engineers, risk managers, their quantitative analysts to be able to pick up the tools of quantum computing? And this isn't something that you can do overnight. You can't take an organization from zero quantum expertise up to building enterprise-grade, high-trust solutions for their customers within a couple of months. They recognize that this is a journey over many, many years and will take some time to get the people, the processes, the tools, the policies all in place to be a leading technology bank in the Asia-Pacific region. So what QBranch has built in partnership with the Commonwealth Bank, and we delivered to them earlier this year, is a quantum computing simulator environment and developer toolkits that run on premises within the bank's cloud, so deployed on the enterprise cloud, their private cloud, and it allows their software engineers to explore and to validate some of the applications of quantum computing that they're interested in within their normal development environment. So they get access to their own data, they don't have to shift anything around, they're not going outside of the bank's firewall, they get to use the programming languages that they used to, the development environments for configuration control and testing and all the normal things that make enterprise software kind of challenging. But they get to look at the potential applications of quantum computing and to explore how they might use that in the future. And the idea behind simulation is that we use a classical high-performance computing infrastructure, in this case it's a private cloud at a bank, to simulate the behavior of the eventual hardware. Now there's some limits on what we can do with that in terms of performance, but for the most part we can teach and explore the basic functions of quantum computing in a regular kind of environment. And so over the past year or so, QBranch has delivered with CBA and a few other partners. We're teaching people how to pick up the tools of quantum computing through educational events, and one thing we do in particular is run quantum computing hackathons, where it's a one-day event. Regular software engineers, data scientists with no quantum background whatsoever come in, we deliver Quantum Computing 101, and then we show them how to program a quantum computer, and then set up a competition where it's like throughout the rest of the day, teams working together, work through a series of problems, each more difficult than the last, and hopefully get to the end of the day and win a prize. We'll have some beers at the end. And by the time people walk out the door at 5 p.m., they've gone from zero quantum computing knowledge to at least having the fundamentals and having hands-on programs and quantum computing applications to take back to their organization. What that has unlocked for us is an opportunity to develop some of the early applications of quantum computing. By running hackathons and training events that get tools into the hands of regular developers, it gets them thinking about the problems in their day-to-day life and how quantum math can help solve those problems. And so that's led to a number of engagements for our company, where we're now doing design and build activities on particular problems that were identified during those hackathon events, where quantum maths and the quantum computing approach could apply to that real-world problem. And so this is the challenge for all of us, that we might have this magic technology, this breakthrough technology in quantum computing, but unless we can get into the hands of regular software engineers and regular developers that are already within enterprises and organizations that have that domain knowledge, it's going to be a very rough road indeed. We need to unlock the potential of people's domain expertise and get tools into the hands of developers so that they can create applications there. So I'll leave it there. Thanks again for the invitation to be here today. I look forward to questions.
Thank you, Michael. Thank you, Michael. Next, we have Altaf Carim from the Department of Energy.
Thank you. Let's get situated here.
We have to get the routine down. We don't allow it in the future.
Do we have the slides? Thank you. Well, good morning, everyone. Thanks for the opportunity to join this event. It's been a really interesting morning so far. I'm looking forward to the rest of the day. I'd like to speak, as the slide says, in terms of quantum information science more broadly. So certainly including, but not limited to, quantum computing. And I'd like to give some background and context on U.S. federal activity. We'll say a little bit first on the overall interests and interagency coordination in this area, and then discuss the mission, the scope, and the resources of the Department of Energy, and particularly the DOE Office of Science, and go into more detail on the Office of Science perspective and activities in QIS. Well, why are federal science and technology agencies interested in QIS. You've certainly heard some good reasons in the previous talks, but in fact, the opportunities that arise from processing information that is uniquely quantum, that involves and makes use of superposition, of entanglement, of squeeze states, go well beyond computing. I've listed some here in some of the categories you typically see. This is not by any means an exhaustive list. In addition to applications in numerous areas, we've only explored the tip of the iceberg with respect to both the fundamental science of QIS itself and also the ways in which it can impact basic research and understanding in other fields. So both the fundamental and the applied research literature, which is the graph you see here, continues to grow dramatically. So this is publications from 2000 to 2015, with the three curves representing quantum information, communication, and computing. So even as initial niche applications are starting to be realized in some of these areas, the fundamental work continues to expand. I promised you I'd say a little bit about the interagency aspect of this. How does the federal government deal with this? There is an interagency working group on quantum information science. It was created as a formal subgroup of the National Science and Technology Council. That is a cabinet-level body that is really the main point where interagency coordination and planning takes place. There are other avenues, of course, as well, but this is at the highest levels. So this is a sub-body of the NSTC. It's been meeting regularly since October of 2014, so for about 3 years now. And the various agencies that are participating are listed there: Department of Defense, of Energy, NIST, you heard before, National Science Foundation, National Intelligence Office, and then offices within the Executive Office of the President, including the Office of Management and Budget and the Office of Science and Technology Policy. Some of the functions of the Interagency Working Group are listed below, certainly sharing information on existing programs and discussion about developments in the field and how that might inform future planning. The group has issued some public requests for information at various points, has also held a couple of workshops. The two that I've listed have been at NIST and have focused on industry perspectives. And in addition, there was a publication of a major report, a National Science and Technology Council report that this group put together in summer of last year. So I'll say a little bit more on that in this next slide. So this report came out July of last year on advancing quantum information science. What are the national challenges and opportunities? It's deceptively short. We tried very hard not to make this a tome that would be difficult to read through. The actual text is only about 10 or 11 pages. But it really tries to boil down what we're seeing at the time as the current impediments to progress, what does the path forward look like, and to make the case for this being an important area to look at and important to the missions of the various agencies that were involved. So as you see, some of the things we were concerned about were institutional boundaries, the education and workforce needs. How do we do knowledge transfer, technology transfer with so much fundamental research still going on? Do we have the tools for materials and fabrication? Do we need new materials? Do we need new capabilities there? And can we ensure that we have not just an appropriate level of funding, but stability of that funding? In some senses, that's almost more important than having greater amounts of funding. This is the title. The title is Advancing Quantum Information Science, National Challenges and Opportunities. and it's a report out of the National Science and Technology Council. So the path forward we suggested really required that we have stable and sustained core programs that were then supplemented by strategic targeted investments, and that the field go forward with controlled growth, be closely monitored and coordinated, and that we take an approach that was adaptable because so many things were changing so quickly and clearly still are, and concluded that there should be a priority for federal coordination and investment. So to shift gears a little bit, this is the interagency context that we are in, and I wanted to say a little bit about the Department of Energy Office of Science, first of all, what it is and what it's about for those of you who are less familiar with it, and then talk about specifically the Office of Science's interests in quantum information science. So broadly, the mission of the DOE Office of Science revolves around delivering scientific discoveries and major scientific tools that can help to enable those discoveries in order to transform our understanding of nature and advance energy, economic, and national security in the U.S. There are 6 scientific program offices within the Office of Science. It's a little confusing with the terminology because these are also called offices within an office. But if you think of them as programs, maybe that works better. There's advanced scientific computing research, basic energy sciences, biological and environmental research, fusion energy sciences, high energy physics, nuclear physics. You might look at this list and say, well, only 1 or 2 of these have anything to do with quantum information science, and that's where you'd be wrong, because most of these offices are actually deeply involved in looking at where we go with quantum information science and what it can bring to their missions and their disciplines. So still talking broadly about DOE Office of Science, just to let you know in terms of both research and resources, a few sort of facts and figures. The Office of Science alone provides about half of the total U.S. federal support for basic research in the physical sciences. So it's almost as much as all other agencies combined in this area for National Science Foundation, NIST, Department of Defense, and many others. In total, it supports somewhere around 19,000 individuals, ranging from PhD scientists through graduate students and support staff, engineers. One key role is maintaining U.S. and world leadership in high-performance computing, although it's not the only role. And it continues to be the major U.S. supporter for physics, chemistry, material sciences, and biology for discovery and for energy science. In terms of resources, you may know that there are a number of national laboratories around the country. There are, in fact, 17 national laboratories that the Department of Energy is responsible for. There are other types of federal laboratories outside of the DOE system, of course. NIST is one example. But the Office of Science serves as the steward for 10 of those 17 national laboratories, and that represents a lot of resources and a different kind of resource than one might find in academia or in industry. It maintains the largest collection of scientific user facilities of research infrastructure operated by a single organization anywhere. And that infrastructure is used by more than 32,000 researchers every year. And I've shown some examples down below in terms of light sources, observational networks, nanoscience centers, high-performance computing, and there are others as well. So let me now focus in a little bit more on quantum information science and talk about DOE's interests and the Office of Science's interests. First of all, in how do we use what the Office of Science has in terms of research and resources to advance the field of quantum information science. And firstly, in terms of fundamental science, we're leveraging work that's already been established in both DOE national labs and Office of Science supported academic groups to maximize the impact. I've shown a number of pictures here because pictures are more interesting to look at than words. I obviously don't expect you to read the text below them. But essentially, just as some examples, the first has to do with simulating quantum computing, and in this case, simulating a 45-qubit quantum computer. So this is a simulation run on a conventional computer, but that's really a big step forward to be able to simulate that many qubits working in tandem. So this was done at one of the Office of Science user facilities not too long ago. The second illustration is of a topological insulator with a superconducting layer on top. This is for producing a particular type of qubit that at this point has not yet been realized, at least not to my knowledge, but that holds a lot of promise because it's a particular type of qubit that is less prone to error than other types, although it has, as you might expect, some compensating disadvantages. The third image really reflects interest in theory as well, and how does the theory work that has gone on in other branches of science inform how we move forward in quantum information science, and vice versa. And some of that is through tensor network approaches for understanding entanglement and topological order and other aspects. And the fourth shows hardware again. In this case, it's an ion trap, and you heard a little bit about ion traps earlier. So this is a laser-cooled and confined ion trap at one of the national laboratories. Going a little further in that theme, there are also the tools, the equipment and instrumentation that come from the DOE Office of Science programs. There's certainly a lot of knowledge as well as experience and physical hardware in these technologies for enabling some advances. Again, you see a different kind of ion trap now. This is one that is really a unique capability that's been developed at Sandia National Laboratories, and that Sandia provides these ion traps to a number of researchers at other institutions. The second has to do with a different type of qubit technology. These are nitrogen vacancy complexes in diamond, which have some unique properties and may be of particular interest for other kinds of applications than computing, for things like imaging and sensing. And the third has to do with supporting technologies, in this case, superconducting radio frequency cavities, a variety of which are produced, and the experts in this are all at the national laboratories. These are some cavities produced at the Fermi National Laboratory, National Accelerator Laboratory. In terms of interests as to what quantum information science can do for science more broadly, here's a little bit on quantum computing applications for identified grand challenges in the areas that the Office of Science is interested in. These are areas that we think could really be transformed, looking at quantum many-body systems for materials discovery, for chemical processes, including catalysis, for nuclear matter equations of state, for simulating field theory, for the very fundamental aspects of physics, high-energy physics and nuclear physics that look at quantum dynamics and quantum field theory. We can learn things by using quantum systems we can control to simulate quantum systems that we would like to understand but can't directly control. Machine learning is something that we may see some really interesting advances in with quantum approaches for looking at large data sets, such as those produced at large physics experiments, for inverse molecular design, for biological purposes, and for optimization and prediction of other biological systems. So we see a lot of areas that are important, and these involve partnership programs across these various offices within DOE's Office of Science. In terms of some of the initial research, there were two program announcements put out last year, as you see on the left-hand side of this, by the Office of Advanced Scientific Computing Research. These were attempts to establish quantum algorithm teams and a quantum testbed pathfinder approach. And in FY17, the initial awards were made in these, so 3 interdisciplinary teams in the first case and 2 in the second, led by national labs, but including a variety of partners were selected for some initial work. There have also been pilot projects in terms of research at universities. You see a couple examples listed there. One does have to do with machine learning in order to separate signal from background in identifying the Higgs boson, which many of you, I'm sure, have heard a lot about in the past few years. And understanding how to collect those signals and identify that needle in that haystack of particles is a really valuable advancement, and you'll be seeing 1 or more publications come out on that in the near future. And some other work at University of Maryland that has to do with simulating particle scattering with quantum algorithms. And kind of the last substantive slide, in some senses, I'm going to put up is saying, okay, let's look beyond computing once again and talk about some of these other applications. And here's just another variety of things that we're looking at in terms of sensing and microscopy and how that can address using quantum approaches, quantum sensors that make use of entanglement and or of squeezed states, and other types of approaches to do all kinds of different things, to enhance X-ray spectroscopy, to do single photon detection, single photon emission, for environmental sensing out in the field in some cases, for looking at gravity and other forces I haven't really mentioned, but some of the very near-term applications involve accelerometers, gravimeters, measuring those kinds of things with quantum sensors, and even quantum electron microscopy that might allow you to get the kinds of amazing resolution we get currently with electron microscopes, but to do so with much lower doses of electrons, which would be really valuable for looking at sensitive materials, biological materials, and the like. So finally, I have a slide that's titled Summary, but perhaps should be more like closing thoughts or parting thoughts, since it's not exactly a summary of what I've said. But I wanted to impress upon you that quantum information science broadly, including all of these fields, is really recognized by federal agencies as holding promise for a lot of applications and new possibilities in fundamental research. I would say that general purpose quantum computers or universal quantum computers clearly offer the possibility of addressing some of these things that conventional computing can only tackle less efficiently or not at all, but that those types of universal quantum computers may yet be quite a ways off. And there are quite a few technical challenges that remain. We clearly don't even know what type of physical system is the best approach yet. And that's fine. We're looking at many different types of physical systems, as you heard before as well. But that's a phenomenal opportunity, but it may not be a very near-term opportunity. Closer in time, and in fact, being implemented in the present day, are systems for quantum simulation, quantum annealing, and simpler quantum computing systems. And those are having an impact already on the state of knowledge and technology. And there are applications in the areas of sensing and metrology and related types of things that are also already appearing, and there are quite a few more on the near horizon. DOE's Office of Science really has some extensive ongoing research and a knowledge base, as well as resources of various kinds to advance the field of QIS, and it's part of the mission. And making use of QIS advancements to accelerate progress across all of these areas is something we're very interested in. So with that, I'll close. Thank you very much.
Thank you very much. So we have about 15 minutes for questions and discussion. So if you have any question you would like to ask the panelists, please raise your hand and someone with a microphone will come. But I thought I will start by asking you three here, because I think we have a nice mix from academia, government, private industry, and someone with both hats. So far today we've heard a lot about, actually for the past 20 years, we've heard that the quantum computers is 10 years away. And we still hear about that today. And we've heard today applications that are in the short term and other applications that are in the long term. It's been mentioned a couple of times that maybe applications, the threat to the cryptographic infrastructure might be on the very long term. So I'd like to sort of have a synthesis of all this. You don't have to put timeline numbers, but I'd like to see and hear what would come first. Like what kind of benefit will come first? And also we hear about this thing called a quantum supremacy, which some people are claiming is going to arrive by the end of the year. So when will a quantum computer be useful? What would it be useful for? And sort of how far down the road or how complicated it will get to the point where it might become a problem for the cryptographic infrastructure. So it's a loaded question, but that's the whole goal of having a discussion.
Well, yeah, when the field started a long time ago, there were quantum computers in the 90s, but they were trivially small, involving just a few qubits. And I would say you could argue that 30 qubits is also trivial in the sense that we can, I think, as you mentioned, we can simulate the full performance of 30 qubits classically. And so this notion of quantum supremacy has come about because when you get to a magic number of 50 or 60 qubits, that's when classical machines fall flat. And what's tricky in the field, a few things I'll say. One is that the first use of 60 qubits that are called quantum supreme will almost certainly be useless. In other words, it's more of an academic endeavor saying, look, this thing can do something you can't simulate. It won't be useful. It certainly won't be useful. But again, academically, that's good. It's a roadmap along the way. I'll also say that when you claim something is quantum mechanical, it's a slippery slope because this is quantum mechanical. Every piece of it is. Is that a quantum computer? Well, now you're getting into arguments of definitions of words and so forth. So I guess I can sort of, I think maybe we should step back and say, can it do something useful? Who cares what you call it? And there are well-known quantum algorithms, and if you can program them in a way that's useful to find some answer to some chemistry problem, for instance, that will happen. I didn't mean to take so much time here, but what's really interesting in the last several years, as we all know this, is that industry is playing a major role in this field now, and that wasn't true 10, 15 years ago. And to me, it's exciting because that means we're going to, as Michael said, we're going to have devices where the user doesn't have to know or care what's inside, just like your iPhone. Who knows what's inside? Who cares? You use it. It's useful. And quantum computing, I think we're going to have small, useless machines that at least the user can use without having to know what's inside. And I think that's a required step to get to the next stage, which may be 15 years from now, where we actually have systems that users can run that are useful and doing useful problems.
We could all go home this afternoon and go onto the IBM Quantum Experience and use a quantum computer today. It's a very limited capacity machine, but it is a genuine quantum computer that can solve some of the types of algorithms that Kris was just describing. And I think what's so exciting about where we are today as an industry is we're seeing this transition from government and university-led R&D to more commercial development. So all of the major investments into quantum computing over the past 3 years or so have come from a lot of commercial interest in what's possible with a quantum computer. And so we're seeing that transition, which makes it exciting for companies like mine that get access to the very early stage hardware that wouldn't be commercially useful at all, but we can start to explore and to validate what those applications are going to look like. And get ourselves to the point where, as I described before, quantum computing in the cloud with a credit card, where you won't even know that you're using a quantum computer. You'll just be using an app in the cloud to drive something on your iPhone or your autonomous vehicle or something in your enterprise. That's the vision, that you won't even know that quantum computing is a part of your life, but it's underpinning a lot of that advanced algorithmic work that you make use of.
So I would make a couple points here, and I'm kind of picking some things that have some variety to them. They aren't necessarily connected thoughts. One is that there is, for any physical instantiation of a qubit, right? A qubit is a concept, and there are various physical ways to realize those concepts. But for any physical or technological instantiation of a qubit, that qubit is effectively also a quantum sensor. And one of the reasons that quantum sensing applications may come along earlier, and have been coming along earlier, actually, certainly in navigation, in precision time measurement, in some other related areas, is that in those cases you don't necessarily need a networked set of qubits, but individual devices can provide you with important information that's not accessible by other means. So that, in terms of some of the time scale of things, would be one comment. Another thing that has not been brought up today, and I'd like to poke the two experts to my left to say a little more about, perhaps, is the distinction between a physical qubit and a logical qubit. In that, when you talk about 300 qubits giving you 2 to the 300 states, that's only true if you have 0 errors. And it may take many, many more qubits to correct errors than it does to deal with the base information. Or there may be other ways to go about error correction. I don't know if either of you would like to comment any more on that.
Sure, I can jump in. Yeah, it wasn't mentioned. It was, I think, in one of the introductory talks, maybe in Warner's talk, he talked about something known as error correction, which is probably as important as Shor's algorithm more than 20 years ago, showing that actually quantum bits, they look like analog computers because they have this superposition. It can be 90-10, 50-50, and there's a continuous variable that describes the system. And when you put lots of qubits together, there's exponentially many continuous variables. And we know analog computers are not stable. We use digital electronics because they latch. It doesn't require, when you have a 5 volt or 0 volt signal, if the signal droops to 4.5 volts, you look at it and say, well, that was 5. And then you bring it back up to 5. That's feedback. Well, in a quantum system, when you measure it, it gets destroyed. So just the academic idea of quantum error correction is really subtle. It exists, it works, and it requires a lot of overhead, and it's actually, some computer purists would say that was the beginning of quantum computing, when it was shown that quantum systems latch. On the other hand, I would say if you had 300 qubits, you're probably not going to do anything with more than a few thousand operations. So if you can get passively stability at the part per thousand or maybe 100 part per million level, then you probably don't need error correction. And the overheads are severe. If you want to fully, what Altaf means by a logical qubit is one that's been beefed up by other qubits for error correction. You redundantly encode. There's a huge overhead, 100 to 1, 1,000 to 1, maybe even more. So for 300 logical perfect qubits, you actually had to have 300,000 physical qubits, and they were encoded in a certain way. And the overhead is so severe that I guess I would call into question, if you only have 300 qubits, do they need to be logical qubits? Because you're not going to need to carry them that long. And so, unfortunately, in the next 5 or 10 years, we're not going to have 1 million physical qubits to do error correction. So right now, I would say error correction is largely an academic subject. It won't be used for anything interesting, probably for the next 10 years. People might disagree with me on that, but we're going to get, it's more in the long lines that Michael and I were talking about, that just getting machines into the hands of people, even if they have errors, You have to do that if you ever hope to get to 1 million qubits, and then do error correction.
Yeah, exactly. There are many things you can do with a quantum computer. Some of those things require error correction. Many of those things require error correction. But there are some things that don't require error correction. And so that's where we as a commercial company focusing on enterprise use cases, that's where we're trying to focus, is the non-error corrected applications of quantum computing. And thankfully, they fall into some really valuable areas of study: optimization, machine learning acceleration, and quantum chemistry. And so we see enough near-term opportunity in those application areas that it's worth pursuing quantum computing as a subject and a differentiator to what we do, even if the error-corrected big-scale computers won't be available to us for at least another decade or so.
Thank you, gentlemen. So why don't we open the floor to questions? So I see one at the back here.
2 quick questions. First, given what we know about the technology of the hardware today, is it subject to miniaturization, or are we permanently locked into a cloud environment, in which case there are enormous communications implications for the evolution of this technology? And secondly, at the risk of expressing a personal opinion that might get you into trouble, could any of you tell us which are the principal institutions globally, because you've mentioned institutions have popped up from time to time, everybody mentions, but which are the principal institutions, both commercial, governmental, academic, on a global basis, that are working to advance this from theory to reality and application? So, thank you.
So 2 questions here. So anyone who walked into a quantum computing labs noticed that those machines are huge, cold, big magnets, dilution fridge. Are we stuck with this, or is there a way forward to think about maybe having a user case where you can hold it in your hand? And number 2, who are the key players globally?
So on the miniaturization, I would say you kind of answered your own question. In the interim, there's no need to make it super small when you're at early stages, just like we were in the 1960s with mainframe computers. Nobody had one in their house. That said, quantum bits are usually pretty small. Superconducting qubits aren't all that small, but they're 1/10 of a millimeter or something. And when you put lots of them together, they occupy some volume. And the technology I work with, individual atoms are very small, and they're only a few microns apart. Again, the space occupied by the qubits is not so much; it's the control system. Like what I said, putting that hard wall, isolating the system. The infrastructure there is it's actually not usually quantum. Like the dilution refrigerator is a classical object. Lasers are classical. Vacuum chambers are all. So these are things that exist, and if there's a motivation to make those things smaller, they will be made smaller. But I don't think there's a motivation yet. When you get to millions of quantum bits, yes, there will be more of a motivation to shrink. I don't know if they'll get as small as a phone, but maybe we'll move on to the global. There is another session in the afternoon where we'll talk a little more about international exposure to this field, but if you want to.
Yeah, just to cover off the international scene quickly, and my belief is that the US has demonstrated tremendous leadership in this field over the past 30 years, particularly through the research funding mechanisms that go into organizations here, but the world is investing as well, and we've seen significant investment from essentially the Five Eyes nations, so Australia, Canada, the UK, all have hundreds of millions of dollar programs going into quantum computing research as well. The EU is working on what they call the Quantum Manifesto, which is a €1 billion plus program over the next 10 years to accelerate quantum computing research there. We saw some announcements last week between Intel and researchers at TU Delft on working on quantum computing hardware. Not to be outdone, the Chinese announced last week a $10 billion research center into quantum computing, backed partially by Alibaba. I mentioned the large cloud providers before. Ali Cloud is one of the largest cloud providers in Asia, and that's a partnership with the Chinese Academy of Sciences as well. So an enormous amount of new money going into R&D for quantum computing. I think the fundamental and applied research that then can feed into what we're doing on the commercial side is incredibly important. and particularly in generating that workforce that we need that understands the kind of equations that we saw on the board at the beginning this morning and can turn those into to commercially useful outcomes.
Anyone else for a question?
My question is for Altaf. Your interagency working group on QIS, I saw DoD was there, but I saw two names that didn't pop up. One was NSA, and the other one was DHS. Now, I know that NSA is keenly interested in issues having to do with quantum, particularly post-quantum cryptography, et cetera, et cetera. Can you give us any idea about the work that your office does and DOE does in terms of interactions with both NSA and DHS? Are they following closely, tracking closely the work that you guys are doing on quantum computing as part of what's going to be their input in dealing with it from a national security and domestic security point of view?
Yes, I think they are, and they're well aware of the working group, and there's been some involvement and participation, not on it perhaps as regular a basis as some of these other agencies. But there's good communication there, and some of that communication happens through the working group. Some of it happens at the White House level through the White House offices and other mechanisms.
I think the beauty of the U.S. system compared to some of the other global players is its diversity of mission. The NSF is more the pure science, also DOE, basic energy science. DoD, of course, has historically funded lots of basic research, including quantum in this country. But the intelligence community, which historically hasn't funded physical sciences over the last 20 years, are actually by far the top supporters and funders of quantum computing since day one, clearly because of the factoring algorithm. And one agency that has been mentioned is called IARPA, which is the intelligence version of DARPA. And they've had a long-standing program for the last 15 years, even they were different names back then. And again, we talked about error correction. They have a very targeted program now, which is to build a single logical qubit, just one with maybe 20 qubits. And the performance they're asking for are the same metrics that you need to build a big system. So it's actually an interesting program, even though its target is very, very narrow, something they can measure.
So unfortunately, we ran out of time. So thank you, gentlemen. All of us will be here for the rest of the day. So if you want to come talk to us or ask more questions during the breaks, you're more than welcome. And enjoy the rest of the day.
Very good.